Good evening.
Good evening, sir.
Okay, so we'll wait for 5 more minutes and then we'll start. How your preparation is going on? Forget
Good, sir, but we can extract to metallurgy problems, sir.
extractive metallurgy. Okay,
Theory part, I'm okay with that. Only problems, I find it difficult to do.
and that numerical problem.
Yes, sir, like mass balance, material.
Okay. Okay, so today also I will solve one mass balance problem related to extractive metallurgy. So that also then you can
Okay, sir.
follow
Sir, I had also another problem, sir, that with units.
units. But that you have to be very careful. Like you should change unit accordingly. Like otherwise you will get a wrong answer even you are following the same approach. So don't solve question in hurry. Just read the question carefully first and then start approaching it.
Okay, sir.
Good evening, everyone. I am audible.
Yes, sir.
Yes, sir. Good morning.
Yes, sir, you are
Okay.
audible.
Okay. So welcome you all to the fourth week of live mentoring session of GATE Phase 2. So now let us move to solve the first question of today. This is the question number 44 of GATE 2012. The question is the fracture stress for a brittle material having a crack length of 1 micrometer is 200 megapascal. Fracture stress for the same material having a crack length of 4 micrometer is. This is a very simple question. Even but just reading the question one time, I think people can answer it. Anybody want to approach?
Sir, 100 MPa.
100 MPa. And others, are you people are saying same or different?
Same, sir.
Yes. So this is a very straightforward question. So this question is you can approach using the equation of Griffith equation for the brittle fracture for the brittle material. So do you know the equation? Can you tell me what is sigma f?
Sir, the sigma f is inversely proportional to root over c.
Yes, the whole equation. What is the whole equation?
So it is equal to root over of 2e gamma upon pi into c.
Yes. So this is the equation, and here you can see that sigma f is inversely proportional to root c. So initially that sigma f was 200 MPa, or you can write is equal to constant term into 1 by root over of c. Initially c was 1 micrometer, and then let's say it is sigma f 2, and then constant into, now the crack length is 4. So this will be 1 by root over of 4. So now from these two equation, you can see that your sigma f2 will be 200 divided by root 4, that is equal to 100 MPa. So do you know based on which concept this equation is derived? No need
Griff.
to go for the derivation, just tell me the concept.
Griffith theory, sir.
Yeah, but what was the his proposal, like what he proposed, and based on which concept he derived this equation?
Sir, the elastic strain energy released is equal to the surface area created.
Yes. So before derivation of this theory, people was calculating the theoretical cohesive strength, and that value is much higher than what is the actual fracture stress. So then Griffith he proposed that brittle material generally consists of very micro cracks inside the samples. So then what happens? Near the micro cracks, the stress concentration developed. So that is the reason that the your material get fractured at very lesser stress as compared to the theoretical cohesive strength, right? So then the, yes, what you said, the concept is based on the that crack will propagate only if the strain energy release is equal to your ki- surface area creation, energy required for the surface area creation. So so this is the concept. This is your total energy. Let's say delta U. So one term will be for the stress surface area creation, and another term will be for the strain energy release. So he proposed that the crack will grow only when your the change in energy will be zero. That means that whatever the energy that is releasing because of the releasing of the strain, that will be equal to the energy required for the creation of the surface, is equal to when this equal to 0. Okay, so I think all are okay with this question. So if no one has any doubt, then we can move to the next question.
Clear, sir.
Okay, Okay, so this is the question number 11 of GATE 2018. At equilibrium, the maximum number of phases in a three-component system at constant pressure is option A 1, option B 2, option C 3, and option D 4. This is also a very easy question. Anyone want to answer?
4, sir.
4. Okay. Others are also agree with it.
4, sir.
Okay. Okay. So based on which equation you are calculating this? Which
Gibbs phase rule.
gives phase rule. Okay. So can you tell me the equation?
F equal to C minus P plus 2, but at constant temperature, so we take plus 1. Condensed phase rule.
F is equal to C minus P plus 2. Okay. But here it is mentioned at constant pressure. So these two is one is for temperature and another one is for pressure. So at constant pressure, your equation will be C minus P plus 1, right? So now the number of component is 3. So C equal to 3. And at equilibrium means your F value will be 0, right? So now if you put these values in these equations, then you will get 0 is equal to 3 minus P plus
4.
1. So P will be 4, right? So this is a very easy question to solve. But anyone, anybody want to approach how to derive this phase rule? Anyone know the derivation of it? How this equation came or that phase rule came?
So, like we calculate the number of independent components
Hmm.
and the number of constraints. We subtract that too, and we get the degrees of freedom that we have.
Okay. Okay. Before the derivation, I want to uh, ask few questions related to this Gibbs phase rule. So let us consider one phase diagram. Okay. Sorry. Let's say this is alpha, this is beta, this is alpha plus beta, and this is your liquid. So this will be liquid plus alpha and this will be liquid plus beta, right? So now I will give a few points and you have to tell me what will be the degree of freedom at those points. Here, let's say here, here. So I'm marking the number 1, 2, 3, 4. So what will be the degree of freedom at 1?
0.
0. Why?
Sir,
Just go to the step
invariant
by
phase
step.
rule.
So here what is the number of component? Number of components C is equal to
2, sir.
2. Phase,
3, sir. No,
3 phase.
yes, liquid and alpha and beta, right? Okay. So then F will be 2 minus 3 plus 1 because phase diagram is plotted at constant pressure. So we have to use this equation, right? So in this case, your degree of freedom is 0. So what does it mean? Your degree of freedom is 0 means what? This is a invariant reactions, right?
we cannot change both. Like we cannot change the pressure or the temperature or the composition.
Yes, yes. If you are in at constant pressure, then you cannot change any other variable, right? If you change the temperature, it will go to some other region. If you change the composition also, then it will go to some other region, right? So now, tell me what will be the degree of freedom at 2?
One, sir.
One. How? Okay, you are saying one. Any other want to say anything? Abhishek, Achanta, anybody?
Sir, one.
Okay, you are also saying one. And Achanta, you?
Same, sir.
Okay, you are also saying one. Okay, so all of you are saying one. So now let us calculate from the phase rule. Okay, so what is the number of component again? It is two. What is the number of phases here at point two? How many phases are at equilibrium?
One only, sir. Two,
Uh,
two, sir, two.
two. What are those phases?
So one is liquid and one is alpha.
And also beta is also there, right? Here liquid plus alpha is there, and in bottom alpha plus beta is there. So you have total three phases at equilibrium, right? Not two. Are you getting it?
Yes, sir.
Yes, sir.
It is at a boundary between these two region, right? So that means here liquid plus alpha is there, and here alpha plus beta is there. That means three phases are at equilibrium. So then what should be the value of F? It will be zero, right?
Zero, sir.
But all of you said one. Why you people think it is one?
I thought liquid phase is not stable at that temperature.
No, that is also at equilibrium, right?
Okay, sir.
Okay, this kind of mistake mostly at this point and this line here, people mostly make that mistakes. That's why I wanted to cover this thing. So now also it is also a bit confusing, right? Like I'm drawing this line again here. Okay, so this location you have liquid alpha and here alpha plus beta. Okay, so now, if you see that earlier that composition, if you change anything, like if you change the composition, like you go this side or you go this side, that reaction will change, right? So it is invariant reaction from liquid alpha plus beta is forming. So you go anywhere, that yeah, your reaction will get changed. Even if you increase the temperature in the y-axis. So if you go in that y-axis also, so again that you will be in some other region, right? So here it is obvious that you cannot change anything if you want to get this equilibrium. But here you can see in this location and in this location, these two location, so same situation is there, right? So that means same situation in the sense like above it is liquid plus alpha and but at the below it is alpha plus beta. But you can still can change the average composition, that is C naught, C naught 1 and C naught 2, let's say. So then you might think that degree of freedom may be 1 because you can change this composition thing, right? That average composition. So that's why people sometimes think that the degree of freedom is 1 for this for this location, but actually it is 0. If you follow the Gibbs phase rule, then you will get it. So can you give the explanation why it is 0, why it is not 1? If you, even you can change the, you can move along this line and still you will be at the same kind of equilibrium situation, right? Because liquid alpha and beta all will be in equilibrium, but still you have degree of freedom 0. Why? Are we really changing the composition when we are going from this location to this location?
Sir, like if we will draw the tie line, then
A tie line is this thing only.
Yes, sir.
You are at the same temperature. You are not changing the temperature. Let's say if you change the temperature, then you will go to the some other region. If you change the temperature, then you will go either a liquid plus alpha or liquid plus beta. Sorry, alpha plus beta, right? If you change the temperature. But if you don't change the temperature, at the same temperature, still you can change the composition, but still you are in the same kind of equilibrium situation, right? Liquid plus alpha and alpha plus beta. So three phases are at equilibrium, liquid, alpha and beta, right? So, but according to the Gibbs phase rule, your degree of freedom is zero. So then how can you change this? Are you able to change this composition? Or are we doing some mistake here? Like I'm drawing this one. So C1, let's say C1 0, this average composition, and C2 0. So you are going from this location to this location, and this part is liquid plus alpha and then alpha plus beta. That means three phase equilibrium. Three phase are at equilibrium. You have two component. Okay, phase is three. So you have degree of freedom is zero. But still you are going from this location to this location without changing the temperature. But you are changing the average composition, but still you are at the same kind of equilibrium. So but the degree of freedom is zero. So how we are able to do this thing? Like we are going to the same thing, same. Okay. uh okay, so that's why I wanted to see that all of you are clear with this or not. So now I will go for the derivation. I think after the derivation, this concept will be much more clearer to you people. Okay, so I will ask the same question again after I will drive this Gibbs phase rule. I think then you people will be able to answer this. Okay, so now let's go for the derivation of Gibbs phase rule. So let's say you have a system which has C number of component. Okay, C n number of component. Let's say C1, C2, C3, and dot 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 up to n number of component. And you have a phase of P n number of phases. So P1, P2, P3, P4, and then up to Pn. So now, what is the total number of variable to define this system? If you want to define this system, what are the variable you have to mention? What are the total number of variable? Anybody? One is temperature, another one
Temperature,
is
pressure,
pressure.
and composition.
So this I think you people know. This two is there, and one more thing is there. What is this?
Compositions.
Composition, right?
Composition.
So composition, for composition you have not only one component, you have n number of component, or let's say C number of component. Okay, don't write it as n, it will be like, let's say C number of component. Okay, so your C number of component. So how many composition you have to give then? C number of component, that composition of 1, composition of 2, composition of 3, and composition of, like, C number of composition then you have to give, right? But also you have P number of phases. So it is not the composition of only one phase. It is, you have to give the composition of all the phases, right? For P1, for P2, for P3. Okay. So total how many variables will be there then? P into C, right? C number of composition you have to give for P phases. Again C number of composition you have to give for P2 phases. Again for P3 phases. And like this up to P n number of phases you have to give the composition of all the phases, right? So that means that you have to give the composition of all the phases. It is not like you have to give the average composition. Are you getting my point? How many phases are there? You have to give the composition of those phases. So that means how many variables are there then? Composition, how many composition variable is there? P into C, right?
Only one, sir.
One, how?
Only one phase is present.
No, I am saying that there is a P number of phases are present. P1, P2, P3, and then Okay, let's not go to the n number of first. Let's say I am giving some number then. I think it will be easy to understand. Let's say you have total. You have a ternary system. That means three component is there: component A, component B, and component C. And you have three phases: alpha, beta, and gamma. Okay. So now in this case, for alpha phase, in order to write the composition of alpha phase, how many composition I need to know? Composition of A I need to know, composition of B also I need to know, and composition of C also I need to know for the alpha phase, right? Are you getting my point?
Yes, sir.
So for alpha phase composition, you have to tell, let's say in this case, let's say the composition of alpha is, let's say, 0.2% of A, 0.3% of B, and 0.5% of C. Okay. So we need to tell the composition of three component A, B, and C, because you have three component system here. Now for the composition of beta, it will not be similar to composition of alpha, it will be something different. So in that case also you have to tell the composition of A in beta, composition of B in beta, and composition of C in beta. So let's say for this, let's say the composition of beta is 0.1, composition of composition of B in beta phase is 0.5, and composition of C in beta phase is 0.6. Sorry, zero point 0.4. Let's say. So like this, similarly, you have to give the compositions for gamma also. So composition of A, uh, amount of A in gamma, amount of B in gamma, and amount of C in gamma. So how many composition you have? You need to provide here. 3 plus 3 plus 3. How much? 9.
9.
So that means 3 number of pages and 3 number of component. So 3 into 3. Right? So that's why you had to give the 9 total variables you have to give to define the system. So 9 into 9. Okay. 3 into 3. So similarly, if you have p number of phases and c number of component, then what it will be? It will be p into c, right?
Sir.
This is the composition variable. So then, so it will be p into c. So now you have total variable. How many? Total variable 2 is for temperature and pressure, and then p into c. So now I think you have noticed one thing here. When you are giving the composition or you are writing the composition, you can in we generally tell the composition in terms of mole fraction, right? So the summation of the mole fraction will be 1. Always it will be 1. Agree?
Yes, sir.
So here also you are seeing that if the composition of A is 0.2, 0.3, then it will be composition of C will be 0.5. So let's say if we tell the composition of these two only, we will know the composition of last one. Similarly, if we know the composition of these two only, we'll know the composition of last one. Similarly for here. So we don't need to give the composition of all the three, because last one or one component will be always dependent to the composition of the other two, right? So this is the constant. This is one constant. Composition constant. One will be always dependent to other compositions. Like if you know the composition of A and B, you can easily tell the composition of uh, how many mole fraction of C is there, because total mole fraction is always 1. Summation of the your mole fraction is 1, right? So in this case, what will be your total number of independent variable? This is the total variable. Now independent variable total independent variable will be 2 plus p into c minus 1, because if you have c number of phases, c number of component, then you only need to know the composition or amount of or mole fraction of only c minus 1 number of component. The other last one or the other component which will be present, it will be automatically dependent on the mole fraction of the other component, right? Up to this point it is clear.
Yes, sir.
If anyone has any doubt, you can ask at that point only. Otherwise, it will be more confusing at the end. Up to this, everyone okay? Everyone is okay? Sanjit, Achanta?
Yes.
Okay. So this is the total number of independent variable. So now another constant is there. So that is the equilibrium. Now we have a C number of component. So those are in that equilibrium, right? Sorry. Then up to C. And then in this side also P1, P2, P3, then up to P5. Okay. So what will be the condition for equilibrium for this system? What should be equal if if let's say alpha and beta are at equilibrium?
Chemical potential.
Yes, tell.
Chemical potential, sir.
Yes, chemical potential of how we can write chemical potential of alpha, chemical potential of A in phase alpha is equal to chemical potential of which element? A or B?
B and alpha.
No, it also have to be chemical potential of A in beta. Like you have two phases, right? A is there, B is there. A is there, B is there. It is alpha phase, it is beta phase. So you cannot compare the chemical potential of A with chemical potential of B, right? You have to compare the chemical potential of A in this phase with the chemical potential of A in that phase. You cannot compare with B because that is a totally different element, right? So your chemical potential of A in alpha phase, in that means in this side of your phase, should be equal to the chemical potential of chemical potential of A in beta phase, right? Understood?
Yes, sir.
I think in my previous session also I have shown the proof of this thing also, how this thing is
Yes.
happening. You can follow that lecture also if you forgot. Okay. So similarly for component B also you can write mu of component B in alpha phase is equal to mu of component B in beta phase, right? So now this is for if you have two component system and two phases only. Now in this case we are in general we are considering we have C number of component and P number of phases. So that means in this case what it will be mu of component 1 in phase 1 is equal to mu of component 1 in phase 2. So this is one equilibrium, right? If the P1 and P2 at equilibrium phase 1 and phase 2, then mu of component C1 will will be equal to the mu of component C1 at phase 2. Similarly for if phase 2 and phase 3 is at equilibrium, what will be the relation? Phase 2 and phase 3 if it is at equilibrium then it will be uh, mu of component 1 in phase 3, right? So that means I am writing it here, it will like look, looking very bad there. So mu of component 1 is phase 1 is equal to mu of component 1 is phase 2 is equal to mu of component 1 in phase 3 is equal to mu of component 4 in phase 4. Component 1 is phase 4 is equal to dot 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 mu of component 1 in phase P. Similarly for the component 2 also you can write in similar way. Component 2 in phase 2 is equal to mu of component 2 in phase 3 is equal to mu of component 2 in phase 4 is equal to mu of component 2 in phase P, right? So like this you can write total C number of equations, C number of relations, right? So total C number of this side because you have C component C1 C2 C3 dot 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 up to C. And in this side how many is there, how many equilibrium is there, how many this term I am now saying, how many equilibrium is there? This is one equilibrium, this is another equilibrium, right? And this is another equilibrium. So that means one equilibrium, two equilibrium, three equilibrium, four equilibrium, like this up to how many it will go? Anyone?
Number of phases 3.
P? Will it be P or anything else? Let's think in number of some certain number of phases. Let's say you have three component and four phases. Okay, so that means let's say four phases is alpha is equilibrium with beta is equilibrium with gamma is equilibrium with delta. So how many number of equilibrium is there? Is it four? Think, then it will be, I think it will be much more clear. Everyone think and try to answer. Because the concept related to this phase rule has to be clear, otherwise you people will face lot of question which will come from the phase rule only. This is a very basic question or basic concept, but most of the people I saw that people made mistake in these cases. That's why I wanted to see that are you people also making the same mistake or not while you are answering this thing. So this is because you don't know how to the derivation and the concept behind it. Okay, so I will I will say that every one of you please try to answer this thing. How many equilibrium is there in this? Let's say four phases are there and they are at equilibrium. So how many equilibrium is there? It is okay if you are wrong. Like, but just give the answer. Just what you are thinking, just give the answer. There is no harm if you are answering wrong.
So 4.
Okay, you are saying four. Sanjit, you?
3, sir.
Okay, you are saying three. And Achanta, you are saying four or three or two. You are also saying four, right?
4, sir.
Okay. So you have four phases, but when I am asking how many equilibrium is there, that means one equilibrium is your alpha is equilibrium with beta, your beta is equilibrium with gamma, and gamma is equilibrium with delta, right? So total three equilibrium, one, two, three, right?
But alpha is not equilibrium with delta, sir.
Yeah, but all are at equilibrium. So only you have to write three equilibrium equation. As we are writing alpha is equal to beta, beta is equilibrium with gamma, and gamma is equilibrium with delta, it is automatically states that alpha is also equilibrium with delta. You no need to express this thing to know to tell that alpha is also equilibrium with delta, right?
So only we need to mention 3.
Yes, if you mention three, then automatically people will know that alpha is also equilibrium with delta, right? You no need to mention it separately.
Okay, sir.
Like in this case, let's say if we remove any one of this, let's say I remove this one, gamma is equilibrium with delta, then can you say alpha is also equilibrium with delta? No, right?
No, sir.
So if you remove any of these three, you cannot say that all the phases are at equilibrium. But if you just mention three equilibrium, you can say that all the phases are at equilibrium, right? So you only have to mention three, not four, because when you are mentioning three equilibrium, automatically that fourth one will be like considered, right? Similarly, as in the concept of number of component also I told, right? So you have component A, B, and C. If you mention the mole fraction of these two also, let's say mole fraction of A is 1 and mole fraction of B is 0.7. Now automatically you know that what will be the mole fraction of C. You no need to mention the mole fraction of C then, because this is dependent, right? So now you know that if this is 0.1, this is 0.7, that means C will be 0.2, right? So only 2 you have to provide. That's why here it becomes C minus 1, right? That's why it becomes C minus 1. And total number of phases is P, so it is P into C minus 1. So similarly here also, total P minus 1 equilibrium is there, right? And total number of component is C. So total number of equilibrium or fixed variable, that is C into P minus 1. So this is the total number of equilibrium and these are the total number of fixed variable, right? So now your total number of independent variable was 2 into P into C minus 1. So now your degree of freedom, what will it be? Degree of freedom will be total number of variable, sorry, total number of independent variable minus fixed variable. So it will be 2 plus P into C minus 1 minus of C into P minus 1. So you have total variable, and from the total number of variable, these variables are fixed. You cannot change. Are you getting? You have total, you have some thing in let's say 5 or 6 number of apple with you, okay, and for to maintaining the relationship with to your, let's say, your brother, you have to fix uh, around 2 piece of apple, right? Then you have how much freedom, how much your freedom you have, that you can distribute the other number of apple with others. So let's say you have 5 apple and 2 you have to give to your brother. That is a fixed amount, fixed, you always have to give. So now you can freely give other 3 apple to anyone else, right? So similar concept is here. Total number of independent variable is this one, and this is the fixed variable. So then your degree of freedom will be, so that PC, that 2 plus PC minus P plus sorry, minus CP minus plus C. And CP and CP will get cancelled out. So then it will be, okay, I have to erase some part here. Okay. So I'm writing it again here, otherwise it was looking very bad there. So degree of freedom is total number of fixed variable. Two for temperature and pressure, then P into C minus 1, that is for the composition, and this is for the equilibrium thing. What is C into P minus 1, right? So this is the fixed variable and this is your total number of independent variable. It will be 2 plus P into C minus P minus C into P plus C. So this CP and CP will get cancelled out. So now we have C minus P plus 2. So this is your degree of freedom. And this 2 is, one is for temperature and another is for pressure. Now if you fix temperature constant, then it will be 1. If you fix pressure, only pressure constant, then also it will be 1. And if you fix these two constant, then it will be, your equation will be C minus P. Okay. Any doubt? I think now the concept is clear, like how we have derived this equation.
Yes, sir.
Everyone is okay with it? If you people have any doubt, just let me know now. Because now I am going to ask the same question which I asked earlier. So now I think you people can answer from that phase diagram. So this point and this point. So if we move from this point to this point, we are at the same equilibrium, but we are changing the composition. So are we really changing the composition, or are we doing some mistakes here thinking in this way? Because degree of freedom is 0. So there is nothing you can change. All has to be fixed. Your composition has to be fixed. Your temperature has to be fixed. Pressure is already fixed because it is a phase diagram is drawn at constant pressure, that is 1 atmosphere, right? But even if we are going from this location to this location, we are at the similar kind of equilibrium. Now, if you have understood the derivation of the Gibbs phase rule, I think you should answer now. Okay, I will give some hint. So here, liquid is there, alpha is there, and beta is there. Okay. So now, let's say consider this point. So liquid will have some composition, alpha will have some composition, beta will have some composition, right? So at this tie line, I am highlighting it with green. At this tie line, what will be the composition of liquid? What will be the composition of alpha and composition of beta?
Will be same.
No, composition will be of alpha will be given by this. Composition of beta will be given by this, right? Lever rule. Tie line. This is a tie line. This is your average composition. Composition of alpha will be given by this composition, and composition of beta will be given by this composition, right? Not this one. This one. So composition of beta will be given by this composition, and composition of alpha will be given by this composition. Lever rule, you know, right? Am I? Miss, are you getting it, or
Yes, sir.
so? Let's say I am marking this composition is A, and this composition is B, and composition of liquid you will get from this tie line, this up to this and this. Let's say I'm marking with C. So composition of liquid will be what? C, right? Everyone is everyone understood, na? All are silent. Are you people getting it, or have any doubt? You can ask me.
So once tell the liquid
Hmm.
composition.
So for the liquid concentration, you will get from this tie line A, C, and this is C naught 1. So this is the concentration of liquid, and this is the concentration of what? Alpha. So concentration of alpha is A, and what is the concentration of beta? From this tie line you will get A and B, like from this one to this one, and this is C naught 1. So what is the composition of beta? It is B, right? For your average composition of your alloy, that is C naught 1. Now I am drawing another average composition line here and here. Let's say it is C naught 2. Now what will be the composition of liquid? What will be the composition of alpha, and what will be the composition of beta? From the same tie line you can answer, right? Because we are not changing the temperature, so tie line is at the same. Sanjit, what will be the answer?
Yes, sir.
Don't know, sir.
And Abhishek?
Sir, repeat the question, sir.
Uh, so in the first case, that C not 1, your composition of liquid was C, composition of alpha was A, composition of liquid was C, composition of alpha was A, and composition of beta was B, right? Now in the second case, I have taken another alloy whose average composition is C naught 2. In this case, what will be the composition of alpha, what will be the composition of beta, and what will be the composition of liquid? What happens when you are cooling down an alloy? So which composition means from the tie line what you get? Lever rule what you calculate? Phase fraction, right? How much fraction of alpha you will get and how much fraction of beta you will get. But alpha, in let's say in case of iron based system or steel, what is the composition of alpha at this temperature? It will be always same, right?
So 0.02.
0.02, 0.025. So it will be always 0.025, right? Like uh, you have two alloy. So this, let's say this point is 0.025, and now you have two alloy. One is 2% carbon, another is sorry, not 2%. It will be below zero point 0.8. So let's say 0.2%, and this is let's say 0.4%. Now you are cooling it down slowly, okay? And now after some times you are at this temperature, let's say just below, not this temperature, just below this temperature, just below your eutectoid thing. So for one cases you are here, for another cases you are here. So in the both cases you will see the what will be the microstructure? Alpha plus perlite. Am I right? In both cases, this will be your microstructure, right? For both the cases.
Yes, sir.
But what will be the differences here for point 2 and point 4? Phase fraction. Yes. Fraction of perlite and fraction of alpha will be different. Anything else will be different? No, right? Fraction composition of alpha will be same for both both the microstructure, right? For this microstructure, let's say you have alpha phase 1, and for this also you have one alpha phase. For both the alpha phases, your composition of alpha will be 0.025, because almost at this composition, right? Composition of alpha will it be different?
No, sir.
Because you are at the same tie line, right? So when you are cooling this, let's say this is the tie line, this is the composition of alpha and this is the composition of perlite. When you are cooling your alloy up to this point, alpha of this composition will form perlite with this composition, right? But when you change this your average composition from here to here, only the length of your this lever changes. So that means length changes means your fraction will change. These two composition are, these are changing or not? These are fixed, right? Are you getting my point? These two
Yes, sir.
composition are fixed. These two composition are not changing. Only you are shifting from here to here, right? So when you are shifting from here to here, what is changing? Only the fraction of phases, because the length of the lever is changing. Earlier this length was up to this one. Now this length is up to this one. So length of the lever is changing means your fraction of alpha is changing and fraction of beta will change, or fraction of perlite in this case will change. But the composition of alpha and composition of beta are fixed at a constant temperature. When you are at the same tie line, composition of alpha and beta are fixed. So if you see here also, again the composition of alpha and beta is fixed. Composition of alpha and beta is fixed. So your composition of alpha for this alloy, that is C02, it will be A, and composition of beta will be B. Similarly, composition of liquid will also be C. So you can see in the both the cases, composition of your phases same. Only fraction is changing. Understood?
Yes, sir.
So that means, are we really changing the composition when we are going from here to here? Because when we derive the phase rule, what I told, this composition that A, B, C, it is not a composition of your whole alloy. It is the composition of each phases. That's why you are writing P into C, because it is the composition of each phases. Composition of alpha phase, composition of beta phase, composition of gamma phase. In phase rule, that C, that the composition variable we are describing here, it is not overall composition, it is the composition of each phases. So now if you see in this case, when we are moving from this location to this location, overall composition is getting changed, but the composition of your phases, are they changing or they are fixed? They are fixed, right?
Yes, sir.
So then do you have really any freedom here? Because composition are fixed only. It is looking like we are changing the composition, but actually we are not changing the composition. We are changing the average composition. The composition of the phases are fixed. We are not changing the composition of the phases. So at both these 2 points, your composition of the liquid phase, alpha phase and beta phase are remaining constant. Only fraction of changes. Let's say initially you have more number of liquid, now you may have less number of liquid, but the composition will be fixed. So you are not changing the temperature, you are not changing the composition of the phases. So that means degree of freedom is 0, and what we have calculated, that is right. We don't have any degree of freedom at this point. Any doubt? Any doubt? I think you people have still some confusion. Uh, what exactly you don't understand, you can tell me. So I will try if I can explain in better way. In which part you are really facing problem? Anyone?
Clear, sir. From-
Okay. Okay, just remember one thing. When in the phase rule, the composition is we are mentioning the composition. Composition is not the overall composition. The composition is for each phases. If you remember this thing, so then I think your concept will be like, it will be clear. Because earlier we were confusing with the overall composition and the composition of the phases. If you consider the compositions are not exactly the overall composition, it is the composition of each phases. If you see that each phases composition are not changing when you are moving from one location to another location along this invariant line. Okay, so now I will move to the next question. Still I will suggest you people to read this thing once, and if you have any doubt you can ask me in the next session also. So now let's move into the next question. It is also a very simple question. So this is the question number 22 of GATE 2018 Metallurgical Engineering. So the question states that in a A-rich end of AB binary eutectic phase diagram, the solidus and liquidus are straight lines. So what is the solidus line here? Can anyone tell me? This one or this one?
Down one.
Yes, so this is the solid dust line and this is the liquid dust line. So it is mentioned that the solid dust and liquid dust are straight line. So these are the straight lines. Now we have to calculate the filtering range of an alloy with 16% B. So let's say we have one alloy whose composition is 16%, overall composition is 16%. So what is the filtering range?
Sir, we can join this, we can extend this straight line, this eutectic line,
Mhm.
and then, sir, we can use the property of similar triangles.
Yeah, but okay. First, tell me what is the filtering range. Then we will move step by step.
So freezing range is the difference between the temperature at which the liquid is starts and the temperature at which that means that solid starts forming.
Yes, filtering range means at the temperature differences from which your liquid started forming. It started forming the solid and plus liquid mixture, and at which temperature that solidification is not completed. So in this case, it started forming solid from this point, and at this point, the solidification is completed. So this difference you have to find out. So this length, that is delta T. This you have to find out. So there is two option for calculating. Basically, it is a geometry only. So one point is this, one point is this, and this is one point. Okay. So we need to calculate this distance. Okay. So one thing is that you can use the concept of similar triangle. So this uh, A, B, C, and let's say D, E. So triangle A, B, C is similar to triangle D, E, C, right? So that means this length, let's say this length divided by this length if you do. So AB by BC is equal to DE by EC. So in this case AB, A means your temperature is 660 and composition is 0. At B, your temperature is 460 and composition is, okay, let me write in terms of X and Y. So 0 composition and temperature 660. And here also you are extending this line basically. So this triangle, this one and this one. Here also composition is 0 and temperature is 460. And in this point, you don't know the temperature, but you know the composition. Composition is 16, let's say temperature is T. And here your temperature is 460 and the composition is also 16 and this is 460. And at C, composition is 32, temperature is 460. Okay, now what is the length of AB? AB is 660 minus 460, right? And BC is this length, that means BC is this length.
$32.
Yes, 32 is equal to DE by EC. DE you have to calculate, and EC, that is this length from this to this. What is this length? It is 16, right? 32 minus 16. Now you can calculate DE is equal to 200 by 32 into 16. So it will be divided by 2, that will be 100. So what is the length of DE? DE is 100 degrees centigrade. So that means what is the filtering range? Filtering range from this location to this location. That means the filtering range is 100 degrees centigrade. Everyone understood?
For calculating any freezing range, you have to follow this method, sir.
Okay, what calculation?
For calculating freezing range,
Yes.
to follow procedure, sir.
Okay. Other is like s- this is also from geometrical concept only. Like you no need to draw the triangle. You can just consider this line, AC line. So it is a straight line, right? You know the this point, that is 0 comma 660. You know this point also. This is 16 comma TF, or sorry, T start, that is F you can write, or M also, T melting. Uh, so let's say I'm writing this at T, and this is 32 comma 460. So now the slope will be same, right? Okay, let me do it in the another page. 3 point you have. This is straight line. So if you calculate the slope of this straight line, as this is a straight line, so slope will be same from this to this. So now if you calculate the slope using these 2 points, so it will be 660 minus t, that is dy by dx, and then at the bottom it will be 0 minus 16. So it will be equal to the, if you calculate the slope using these 2 points, so that is 660 minus 460, 0 minus 32. Then also we'll get 660 minus t is equal to 200 by 2, that is 1, 232, 100. Similarly we'll get then t is equal to 560. So that means this temperature is 560. So this temperature is 560, and your this straight line, that temperature. So this temperature is 560 and this temperature is 460. So then what is the freezing range? Difference between these two temperatures, 560 minus 460. So that is also 100. So in which way you are comfortable, you can use any of this technique. Understood?
Yes, sir.
Okay. Okay. Now I will go I will solve one question which is related to the mass balance. So this is the question number 2018 of gate to question number, sorry, question number 33 of gate 2018. The question is, iron is produced in a reactor using pure Fe2O3, carbon and oxygen. For every mole of iron produced, 2.38 moles of carbon is used. The exit gas from the reactor contains CO and CO2 in the molar ratio of 1:1. How many moles of oxygen is consumed for every mole of iron produced? So anybody want to approach how to solve this? First go to step go let us go to step by step. So first tell me, uh, what was the initially what elements were, sorry, what compounds or elements were there in your reactor? Fe2O3, carbon and oxygen, right? So this was the your starting point. Now tell me what will be the reactions. What will be the sequence of the reaction? What will happen first? Like what are the reaction that will take place? Basically here you are reducing your Fe2O3 to form
Fe3O4, then Fe2O3, Fe3O4, FeO, and Fe.
No, that sequence you no need to tell. You can directly go up to Fe. But I'm telling like initially you have carbon and oxygen. So first what it will do, it will react with the oxygen. Carbon will react with the oxygen, and it will form CO2. So this is the your first equation. Then this CO2 which is formed, it will again react with the unreacted carbon, because all the carbon will not react at once. So some carbon will also left there, then it will again react with the unreacted carbon, and it will form CO. If we balance, it will be 2CO, balanced equation. Now this CO, this is the your equation second. Now what will happen, this CO which is formed, it will reduce your Fe2O3 plus CO is equal to Fe plus CO2. If we balance, 2 mole of iron is there, so to multiply by 2, 3 mole is oxygen, here 2. So if we multiply it 3 and 3, it will be 3 mole of oxygen plus 3 mole of oxygen, 6 mole, and then 3 into 2, 6. Carbon is also now balanced. So these three equation will follow. First, carbon will oxidize to CO2, then again this CO2 will reduce by the remaining carbon, and it will form 2 mole of CO, and then this CO will react with your Fe2O3, and it will reduce Fe2O3 to form pure iron plus 3CO2. Everybody okay up to this? Any
Yes, sir.
okay. So now what are the information are given? To form 1 mole of iron, 2.38 mole of carbon is used. So at the end, that is the product. At the product, what you have? 1 mole iron. Okay. And the ratio of CO2 is 1. So this we know at the end. Okay. And other unreacted unreacted Fe2O3 may be there. Unreacted carbon may be there. So that we are not considering because we don't know what is the amount. So these two values are given. One is 1 mole of iron is forming, and CO2 ratio is 1 is to 1, and also this thing is given. So now as a starting material, let's say we don't know how much carbon initially was there, how much oxygen was there. So let us consider some values, that is, let's say a mole of carbon was there initially, and a mole of oxygen was there. So nothing else was there, and b mole of, so a mole of carbon was there, let's say a mole of oxygen was there, and b mole of Fe2O3 was there. Okay. So now this is the first reaction. So initially CO2 was 0. Initially CO was also 0. Initially iron was also 0. Initially, and here also CO was, like, I will write it later because already some CO has formed here. So I'll go to the equation, this equation at the later stage. So now let us go to step by step so that it will be easy to understand. So first this reaction will happen. So first this reaction will happen. So this reaction is now let's say x mole of carbon is reacting or dissociating. If x mole of carbon is dissociating, then a minus x mole of carbon will be there, right? And also if x mole of carbon is dissociating, that means it will react with x mole of oxygen, because the molar ratio is 1 is to 1 for this equation. So here also x mole of carbon oxygen will react. How many mole of CO2 will form? Hello? Hello?
Yes, sir.
So how many mole of CO2 will form? Achanta, you can try to answer. If x mole of carbon is reacting with x mole of oxygen, how many mole of CO2 will form according to this reaction? It will be related to the molar ratio only, right? So 1 mole of carbon is reacting with 1 mole of oxygen and forming 1 mole of CO2. Then x mole of carbon will react with x mole of oxygen and how many mole of CO2 will form? Are you people there?
Yes, sir.
So 1 mole is reacting with 1 mole and forming 1 mole. So the next mole will react with X mole, and how many mole will form? X
2
mole.
moles.
X mole, right? Because the ratio is 1 is to 1 is to 1, right? If 1 mole is reacting with 1 mole, forming 1 mole, that means 1 mole is X mole will react with X mole and form X mole of CO2, right? So now this CO2, X mole of CO2 will be the starting material for this reaction. So for this reaction, initially you have X mole of CO2. How many mole of carbon is left? A minus X, because total amount was A. From that amount, X mole dissociated, so A minus X is there. And now in the system you don't have any CO, that means initially it is 0. Now let us consider y mole of CO2 is dissociating. So if y mole of CO2 is dissociate, it will react with how many mole of carbon? Y mole, because the ratio is 1 is to 1. So what will be the remaining amount of carbon? A minus X minus Y, right? And how many mole of CO will form? Ratio is 1 is to 1 is to 2. That means if Y mole is dissociating, how many mole of CO will form? This is simple mass balance, molar ratio.
2y.
2, right? Everyone understood, na?
Sir, no, sir.
2y. Like, uh, this is like simple like mathematics kind of thing. Like, you have 1 mole of something plus 1. This is reacting and these are giving you product of 1 mole. So now you multiply this thing with X or Y, whichever I am considering. So then in this case, X mole will react with X mole and also form X mole. Now for this equation, if you see, this is ratio is 1 is to 1 is to 2. So now 1 mole is giving 1 mole and forming 2 mole. 1 mole is reacting with 1 mole and forming 2 mole. So now Y mole is dissociating. So that means you have to multiply this ratio with Y. I am taking out minus. Y is dissociating. Initially X was there. From there Y is dissociating. So Y is 2, Y, 2Y. So that's why here Y is dissociating. Y, here A minus X was already there. Now again minus Y, we are subtracting minus Y because Y mole is dissociating. And in this case CO, 2 CO is there, that means 2, so it will be 2Y. So initially it was 0, so 0 plus 2Y means now it will be 2Y, right? Now understood?
Yes, sir.
Now in this for the third reaction initially B was Fe2O3 was B mole. And what is the initial now amount of CO? This CO is formed here, right? So now this CO will come here. So CO is 2Y, right? Because this CO is formed here. Now this CO will take part into this reaction. So now your CO is 2Y. Initially iron was 0. Now no reaction has taken place. So now iron is 0. And what is the amount of CO2? CO2 is X minus Y is left. Initially X mole formed and then Y mole dissociated into to form CO. So now uh, X minus 1 Y mole is left. So now it is X minus Y. Now Achanta, tell me from this reaction, if I dissociate Z mole of Fe2O3, so from this CO, how many mole of CO will dissociate? Similar, the ratio 1 is to 3, then equal to 2 is to 3. This ratio it will form. Now I am dissociating Z mole of Fe2O3. So now this will be from how many mole of CO will dissociate?
Minus 3 jet, sir.
Yes, you are right. So in this ratio it will dissociate. So 3Z mole will dissociate. So it will be minus 2y minus 3z. So now how many mole of iron will form? This ratio is 2. That means 2z, right?
Yes, sir.
And how many moles of CO2 will form? Initially it was x minus y. Now how many mole will form? This forming means I have to add it. So plus. How many mole?
3Z.
3z. So now now let us see what are the data were given to us. So according to the given data, now we can calculate. Now we have written the expression step by step. So now we have everything. Like first data was given, that is 2.38 moles of carbon is used. CO2 ratio is 1 is to 1. And how many mole is produced? Iron 1 mole. 1 mole of iron is producing. So now how many from this reaction, how many mole of iron produced? 2z. Right, 2z is produced, and in the question it is said that 1 mole is producing. So that means 2z is equal to how much? 1. That means z is equal to 1 by 2. Understood up to this?
Yes, sir.
Okay, so now another thing is that CO2 ratio. So what is the final amount of CO and final amount of CO2? This is the final amount of CO, that is the unreacted part of CO, and this is the final amount of your CO2 that is formed. So that ratio is 1 is to 1. So what will be the second equation then? 2y minus 3z will be equal to this, means at the end when all the reactions are over, it is told that the exit gas, that after all the reaction your CO and CO2 gas is exiting from the system. So that time the ratio of the gas mixture is 1 is to 1. So that means your unreacted CO is amount of unreacted CO is equal to amount of CO2 that is formed because of your reduction process, because of the reduction of iron. So in this, from these equations, we can see that unreacted CO is 2y minus 3z mole. This has to be equal with what are the total amount of CO2 that is formed, that is x minus y plus 3z. Understood this second equation?
Yes, sir.
Okay. So now already we know the value of z. So z means half. So now we get the relation between 2y and x. So 2y and this side y. So this will be 3y minus x is will be 6z, which is equal to 6 into half, that means 3. So 3x minus y is 3. Now one more information is given to us, that is the total number of mole the carbon that is used. So initially carbon was a, now carbon used, that is x mole used here in this reaction. In any other reaction is there where the carbon is used? Three reaction are there, na? So in which reaction the carbon is used? That means carbon in the left side.
Two.
So two reaction, one and two, right? So in this reaction, x mole carbon is used, and again in this reaction, y more mole of carbon is used. So that means how much from the A was there? From that minus x minus y, it is dissociated. So total x plus y mole of carbon is dissociated, right? Initially it was x a mole, and now it is a minus x minus y. So if you minus it, so a minus x minus y, so that will be a minus a plus x plus y. So this is the total carbon, that is percentage of mole of carbon dissociated. So x plus y mole of carbon is dissociated, so that value is also given 2.38. So you have now two equation. This is 1 and this is 2. 3x minus x is equal to 3. Sorry, 3y minus x is equal to 3 and x plus y is equal to 2. Now if you 1 plus 2, if you add these two equations, so it will be 4y is equal to 2.38 plus 3. That means 5.38. Right? So from this we'll get y is equal to 5.38 minus 4. That is 1.345. Right? I think everyone understood up to this. So now we have calculated the value of y. So and x plus y was equal to 2.38. So what will be the amount? What will be the value of x? Then x will be 2.38 minus y. So it will be 2.38 minus 1.345. How much it is coming? 1.035. Is my screen is visible?
No, sir, it's struck.
Okay.
Screen is visible, but
I think network
now
is. Yeah, camera just I just switch off because that I think the network issue is there. That's why. Okay, now I think it is visible, right?
yes,
So your AX is 1.035. This is your AX. What was the question? How many mole of oxygen? Question was how many mole of oxygen is consumed for every mole of iron produced. So from this reaction you can see oxygen initially you had oxygen A mole. Now how many unreacted oxygen is there? A minus X mole. Right? At the end you have A minus X mole of oxygen. So that means how much oxygen is then dissociated or how much oxygen is used. How many? So that is equal to initially you had A mole of oxygen. Now you have A minus X mole of oxygen. So that means X mole is dissociated and X means 1.035 mole. So this is the your oxygen that is required to form one mole of Fe. Okay, understood. So just write the equation with proper sequence and then use this kind of concept like initially this much was there. Now you just take x or y some variables that this much is dissociating. You have to follow that mole number ratio, that is 1 is to 1 is to 1 for this equation, 1 is to 2 for this equation, and for this equation it is 1 is to 3 is to 2 is to 3. So this ratio you have to look carefully and accordingly you have to write that how much mole is dissociating. So if you learn this writing this like how to write this thing, how the element or how the compound are dissociating and forming how many moles, so then it is simply like you will have few equation and you have to solve those equation and you will get the answer. Understood?
Yes.
Any doubt? Any doubt in any of the questions that are solved today?
clear, sir.
Okay. First question was related to the Griffith's theory for brittle fracture. Second question was the which is covered the concept of Gibbs phase rule. I also showed you the derivation, and I will request all of you to look to read this thing again, that phase rule, so that the concept related to this it get clear. if you have any doubt, you can ask in the next session also related to this question, because this type of question mostly asked in you will face in any kind of interview also, or in the gate exam. Obviously this kind of question will come, but in the interview also people ask this simple question related to the phase view. So it is very important that you people understand this concept. Okay. And the third question was related to the phase diagram. We have calculated the freezing range, and the fourth one is related to the mass balance. So uh, if you have any doubt, you can ask me now. Also, if you want to ask in the next session also, that is also fine. So if no one has any doubt, then I will close the session for today, and we'll meet on the next Sunday.
Okay, sir.
Okay then. Okay.
Thank you.
Good evening.
Okay,
Bye.
sir.
Bye, sir. Thank you.